Hello friends, this is a companion video to one that I believe Mr. Mahalka has just made, where we're going to look at problem 13 in 5.2. An Atwood's machine, one block, has a mass of 5 kilograms and the other a mass of 3 kilograms. Venerable Atwood's machine. I'll call the 5 there and the 3 there. The pulley, which is mounted on horizontal frictionless bearings, has a radius of 10 centimeters. When released from rest, the heavier block is observed to fall 1 meter in 2 seconds without the cord slipping over the pulley. That implies that the pulley is moving with the cord and thus literally and figuratively tying the motion of the pulley to the motion of the moving objects. What is the acceleration of each block? What is the tension in the part of the rope that supports the heavier block? What's the tension in the part of the rope that supports the lighter block? What is the angular acceleration of the pulley? What is its rotational inertia? So this very, very strongly resembles the problem we've done maybe like 4 or 5 times by now in different iterations. We did it as a demo in class. This was essentially the root of the problem in the lab you did, and here it is again, but this time there are 2 masses. There's a mass on either side of the pulley. In previous versions where the pulley was massless, the acceleration of the system depended only on the masses of the 2 objects. But because the pulley now has mass, even if there wasn't one of these objects, the hanging mass can't accelerate with the acceleration due to gravity because, previously, if the mass of the pulley was 0, there would be nothing for this mass to sort of be pulling against, and so it would just fall at gravity at 9.8 meters per second squared downward. But because it's got to exert itself, it's got to exert a force on the pulley to get the pulley to go, the mass of the pulley is relevant. So let's dig in. Really the order of questions kind of walks you through the entire solution, finding one thing at a time. A test and an exam might just jump right to C and D to find things that you would need all the previous bits of information in order to determine. But in order of operations, this kind of walks us through. So in part A, what's the acceleration of each block? Well, since they're tied together, the acceleration of one block and the other block is going to be the same. And so in that case, we're given actual kinematic information about one of the blocks, which would then pertain to the other block as well. They're going to move, they're constrained to each other by a non-stretching spring. So this is going to fall 1 meter in 2 seconds, and assuming that its initial velocity is 0, d equals VOT plus 1/2 AT squared, kinematics, where its initial velocity is 0, that lets us find the acceleration of the 5 kilogram block, and thus basically all the other things as well. So 2d over t squared is the acceleration, which is going to be 2 times 1 meter divided by 2 seconds squared. So that's 2 over 4. That's 1/2 or 0.5 meters per second squared. And so the velocity of the acceleration of the 5 kilogram object and the acceleration of the 3 kilogram object in magnitude is 0.5 meters per second squared. All right, kinematics. A moving object, distance, time, find the acceleration. What's the tension in the part of the rope that supports the heavier block? All right, so for the heavier block, we are investigating the forces on it. We've got its own mass, its own weight downward, and the tension exerted upward. the reason there's tension is because, the string is tied to other things. So it's going to mitigate the acceleration of that block. So it's accelerating downward. So I'm going to call that positive. So we got M5G minus tension 5 equals M5A. We're looking for tensions. So we know gravity, we know the mass, we now know the acceleration. We can rearrange everything and solve for tension. Mg minus Ma equals tension. And I should guess 5. All of this pertains to the 5 kilogram mass. Mg of 5. So that's going to be 50 newtons minus 5 kilograms times 0.5 equals the tension. So the tension upward on the 5 kilogram mass is going to be 50 minus 2.5. That's going to be 47.5 newtons. What is the tension in the part of the rope that supports the lighter block? Almost the same analysis. I mean, conceptually the same, just different directions, different values. We've got the 3 kilogram object is being accelerated upward. So in this case, tension is greater than its weight. So tension minus M3G equals M3A. The tension on the 3 kilogram object is going to be M3G plus M3A. That's going to be 3 kilograms times 10, 30 newtons plus 3 times 0.5. So that's 1.5. So that's going to be 31.5 newtons of tension upward on that one. And so here's where we start to actually get into the rotational part. So far, everything's just been linear. But here's the sort of one of the big conceptual humps is that everything we've dealt with until now has with pulleys, we've assumed that the tension in one direction over the pulley is equal to the tension in the other direction. But that is not true now, and it can't be true. It wasn't ever true, but we just simplified it. But it can't be true because the pulley itself has mass. It requires effort. It requires a net something. In this case, a net torque in order to rotate a thing that has mass. And the only way you're going to get a net torque, a non-zero net torque, is if one torque is greater than the other. And since both of these forces are exerted at equal radii, well, then the only thing that could be different to achieve this is the tensions. So the tensions have to be different in order to get this wheel to start rotating, this pulley. So what is the angular acceleration of the pulley? So this is part D. Well, arguably this could have waited a moment, but because the angular acceleration of the pulley, because the string is not slipping, the pulley is accelerating with the string, and so for a given amount of distance that the string travels, let's say, I don't know, wherever you want to start measuring over to here, for some arc length, usually indicated by a letter S, that's going to be equal to the angular displacement times R. And so if we do this in the same amount of time, if we sort of divide these by time, well, then we have the linear speed, or the velocity, just without direction, the linear velocity is equal to the angular velocity times R. So if we rearrange that ever so slightly, actually we could take that one step. Delta V over T gives us an acceleration. Delta omega over T gives us an acceleration radially, rotationally. So we end up with the linear acceleration, or the tangential acceleration, is going to be equal to the angular acceleration times R. So we rearrange that. Kind of tuck those over here a little bit. So this is the one that matters. we rearrange that, then the angular acceleration is just linear over r. The linear acceleration was 0.5 meters per second squared. The radius is 10 centimeters, so that's 0.1. So we have a rotational acceleration of 5 radians per second squared. And finally, how does this tell us about the rotational inertia of the wheel? So we put this all together back into Newton's second law for rotation. Torque, net torque, equals moment of inertia times alpha. But what we have is information about the torques, and we have information about the rotational inertia, about the rotational acceleration. So we're looking for the rotational inertia. So rotational inertia equals net torque divided by angular acceleration. And we have two torques. We've got the torque generated by the 5 kilogram object and the torque generated by the 3 kilogram object. In that case, or the tension, I should say, the tension caused by the 5 and the tension caused by the 3 kilogram objects. So we've got, let's, for ease of thinking about it, since the 5 kilogram object is accelerating that way, let's call that way positive, and thus, for our purposes, in this problem, we'll call clockwise positive. So we've got the tension times its radius, tension of the 5 times its radius, minus the tension of the 3 times its radius, all divided by the angular acceleration. So we've got the tensions, which we had before. We got 47.5 newtons times the radius, which is 10 centimeters or 0.1 meters, minus 31.5 newtons times, again, same radius, pulling on the same pulley, all divided by 5 radians per second squared. So experimentally, based on its behavior, we are determining how much its rotational inertia must be, or must have been, if this is what happened. 47.5 times 0.1, I could probably have done that, minus 31.5 times 0.1 gives me 1.6 over 5, gives me 0.32 kilograms meters squared. There we go.